Hello. My name's Olly Nicholson. This talk is high art, low cost. Tips and tricks from the field. I'm a field engineer, and what we do is we kind of tour around doing events, talking about Unity technology. We do developer visits. We go and see indie and large enterprise developers all around the world to help them with their art pipelines, things like that. And we also take part in hack weeks and outreach through education. One of the things we get to do is hack weeks. And one of the things we were investigating was how to get AAA quality visual scenes into mobile VR. And that's quite a challenge. Here's two of our favorite Unity characters. And with a little playing around, what did we end up with to begin with? Well, not very much. And why is that? Because of VR constraints. You're dealing with a couple of platforms which really are demanding on the technology that's available. So you're rendering twice, obviously for virtual reality purposes, for both eyes, and you're also trying to target a really high frame rate to avoid the kind of reaction and nausea that you might get from juddering around when you're looking about. So, what happens when you're rendering in VR? This slide basically starts to show you everything that takes time in your game, from the game loop through to the render loop, e.g. what is processed. And what I'm going to talk about to start with is the CPU preprocessing. So this is the kind of stuff that happens first and is taken into account. And then I'll move on down to the kind of optimizations you can make at each of these stages to get things a bit more performant. So we start off with gameplay and physics and AI, and we're also processing all the transforms at this early CPU preprocessing stage. We're also looking at level of detail and allocating the different mesh resolutions for different objects in your game. And we're trying to start thinking about the occlusion culling. Which objects are rendering in front of other objects and therefore occluding? Which stuff do we not have to render to begin with? We also want to start thinking about the dynamic batching, so objects that are dynamic in your scene that can be batched together to do things that are similar and save some cost right there. We also do the CPU skinning at this stage, and the frustum culling to identify what is being rendered in the frustum at any given time. We also set up the sorting, so the order that things are rendered in. So what can we do to try and optimize at this stage? Well, we can obviously make use of the culling API. So we can interact with how we decide things are culled. So an array of spheres with callbacks to notify when you're entering and exiting the frustum. And you can enable and disable that, obviously. You also can consider an optimized character hierarchy. I think Ian touched on that in the last talk. There's actually a checkbox for optimizing the full skeleton mesh down into just the required nodes that are exposed at that point for you to add transform scripts and that kind of stuff. So that's something you can make use of. LOD groups, level of detail groups. The implementation for that in Unity is pretty smooth. You can load in meshes of different resolutions, different texture sets and materials, and control the distance at which they load into your scene. So that's a good stage to think about using LOD groups. You can even disable sorting if you know that that's not actually going to benefit you at that stage. That's an optimization that can be made, ironically. And if you're not bound by draw calls, then don't batch. You don't have to do that if it's not part of your bottleneck. So moving on to the render loop, we're looking at the VR stage. So rendering for each eye. You render one cube for the left eye, and the same cube for the right eye, and then cube 2 for the left eye, and then for the right eye. And so you're doing that whole scene 2 times. So there are optimizations for that, which I'll go into. But you're also thinking about the shadow map computation at this stage. So the point of view of the shadow maps that are rendered into your scene. So what can we do to optimize at this stage? Well, we can have a look at double-wide VR rendering, for example. And that's the concept of rendering that cube on the left eye and the right eye, and then together for both eyes. you can also then start to think about how expensive the shadows are. So if you don't need everything to be rendering shadows, then turn them off. Limit the distance and cascades for these. You can even turn off and on the kind of objects that you want to be casting or receiving shadows. And think about how the scene is laid out and what's going to be seen by any given perspective. You can even think about using simple blob shadows. So if you don't want to actually render the shadows, then cheat. A little decal there that's parented to the object, just as a little example. And of course, in this dynamic example, we're firing these speakables with a shadow that is drawn on the point at which it collides with the ground. So at this stage, we leave the world of the CPU and into the GPU. And this is where the golden rule of avoiding the state change inside the GPU so that it leaves the loop is where it's paramount. So we need to think about reducing material changes. We want to think about reducing the amount of light map changes that happen within your scene. And we're talking about working out the spatial localization, where stuff is in your scene, in terms of how it's grouped together and how it fits together. And then, of course, you've got your send command buffers. The kind of things you can do to optimize at this stage is where we start to think about batching. So batching static objects, for example, so that you are rendering one big mesh instead of lots of little ones. And atlasing your textures. And it's a pretty obvious concept, but if you have lots of textures and materials in different parts of the scene, they're all going to be rendering different draw calls. And what you really want to be doing is combining as much of that as possible into texture atlases. Again, large light maps rather than lots of light maps. So combining big areas into one per room, for example, or per location, and whacking up the size of those light maps instead to combine more of that light mapping data. You can think about material property blocks at this stage, because if you can change an element of a material rather than switching out the entire material, then you can make use of all the kind of stuff that instancing gives us. And multi-threading the rendering at this stage as well. The idea of farming out different parts to different jobs. So what does that leave us with? The final option is to obviously interact directly with the Mesh API, so drawing straight to the screen. That's a complicated thing to do, but if you know how to program what you want to see on screen, then that's the kind of low-level API that you can access. So next stage, we're into the GPU-bound zone. So GPU skinning, and if GPU bound, move the skinning to the CPU, and vice versa. That's kind of the stuff you can help with at this stage. Rasterization, the spherical harmonic lights, and the per vertex lights, are all elements of vertex processing that happen at this stage in the render loop. So optimizations you want to think about here, pretty obvious ones, like using fewer triangles, and again, the concept of using CPU skinning if you're GPU bound. So now we get to the very expensive part, fragment shading. And that's the moment that we fill the screen with pixels. On an average platform, you could probably consider you can fill the screen about 5 times before you reduce performance. So when you draw geometry, if you draw 5 textures on top of each other, that's it. So think about overdraw. Think about what you're trying to put on the screen at any given time. At this stage, you're doing the shadow map computation. You're doing the deferred lighting pre-pass, and you're doing the light mapping, as well as considering the physically based rendering. So when we say physically based rendering, we're talking about the stage where you're trying to understand the physical behavior of your materials. So that's quite an expensive equation. If you're using a BRDF, the bidirectional reflectance distribution function is an equation on every pixel. So try not to use it too much, especially on overdrawn stuff. If you don't need to use, say, the standard shader, try a mobile specular shader or some other optimized shader you might be thinking about, you've profiled. So limiting the overdraw is one of the crucial factors here to avoid a drop in performance. Thinking about overlaying smoke textures that come very close to the screen that are semi-transparent. You're thinking about particles there, you're thinking about foliage, you're thinking about all those things that overlaid start to build up and cost you quite a lot. Control the rendering order with materials and render queues so that you know what is drawn in which order. There's no point in drawing a hugely complicated set of carpet underneath this stage if this stage is drawn on top. So if we control that rendering order, we're already winning. And of course, avoid transparency where you can with things like foliage. If you want to draw leaves and you want to draw branches and that kind of stuff, rather than massive, great big cutout textures, think about simplifying the geometry instead, the shape of the leaf, the shape of the branch, and then the less parts of semi-transparent materials you have, the less overdraw is going to build up in your scene. And then, of course, as I mentioned before, think about cheaper shaders that you can use at these stages. Here's an example of running through the render order. We have a great tool called the frame debugger, and it shows you at which stage each parts of your scene are rendered. So use this tool wisely to get to grips with what is being rendered before what. And then you can actually start to play about with your rendering order and not render stuff that you don't need to render at the end of the day. So at this stage, we have our multi-pass. And for each pixel, you might have to do a second or third pass. Shadow mapping is a second pass in this example. And it's used to apply a shadow map on top of your rendered meshes. With forward lighting, 2 pixel lights are used, for example, on that one triangle. Then that triangle will be rendered twice. So think about how your scene is lit. Think about how the lights overlap with different objects in your scene. If you can space out your lights better and have them cut off before they overlap on certain objects, then you save quite a lot of performance. So you had to do all that in 14 milliseconds. Now, screen processing, you fill the entire screen, and we're at the screen space processing stage. And this is where you want to sort of apply some effects to make your experience look stunning. But it's also a very expensive stage because you're working with the whole screen. There's a series of different post-processing techniques you can use, including our cinematic effects. And the way that you layer them and the type that you use have different expenses. What I could say now is that as little processing per pixel as possible is always ideal. But if you can use our new cinematic image effect stack, you're going to save quite a lot of performance there. You just have to think about the consideration of which of those effects are the most expensive. That order here is roughly an order of cost. So simple color grading and tone mapping through to bloom, AA, and then the very expensive screen space reflections and screen space ambient occlusion. So that's quite a lot to take in. I do apologize. That's enough. So something a little bit more digestible, I can hear you ask. Well, let's start with the recipe card. For your starter, enables static batching and dynamic batching. Just tick the box. Just try it out. See where you go. Start profiling. Disable your shadow mapping where necessary. Bake some of your shadows, but also turn it off and draw it into the textures if you need. Disable procedural skyboxes and all skybox lighting if it's not relevant to your scene. Disable your runtime global illumination. If you don't need bounce light doing crazy stuff all over your scene, very desirable for many effects, but then use it where you need to. Change all your lights to be baked if you can get away with that, and change your emissive shader properties to be baked so that you're not emitting lots of bounce light around the scene that has to be captured by probes or any other real-time stuff. And whack your light map size up to 4096. Just make it huge, and it will use far less of them at the end of the day. For the main course, let's pre-warm the profiler. Let's start using and understanding the order in which things are rendered. And use CPU skinning or GPU skinning, depending on which way you're bound. We can also inspect the overdraw. We've got a scene view overdraw mode that basically allows you to view what is being overdrawn. Or you can use a replacement custom shader of your own to do this kind of stuff. And obviously the frame debugger to watch the rendering order that we talked about. Change the render queues accordingly. That's the best way to think about how you want to render stuff and not render stuff in your scene. It was still not enough. We still couldn't render everything we wanted to render So where did we go? We started to move into the realm of super cheating. But first, I want to talk about the range of perceptions. Because in VR, you're talking about things that are very close to you and things that are very far in the distance. Jason Hickey from Sony came up with a really nice theory that there's a different range of perceptions in VR that you can use to establish how you treat your assets at different distances from the player or the camera. Range 1, 0 to 3 meters. So it's all about the vertices, the detail in the mesh, trying to avoid normal and displacement map at this close stage to the eyes. Range 2, 3 to 10 meters. So using less vertices, but using normal and displacement maps to give the impression of detail, to give a nice look to your meshes that are just out of reach. Range 3, 10 meters to 20 meters. So we start to look at baked shading, only silhouette geometry, and all your components baked in a diffuse if you can. And then, of course, the final range, 20 meters to infinity. So we're talking about imposters and environment maps, things that look like super deep, complex scenes in the distance, but can actually just be rendered into a cube map. So with those sort of foundations, you can start to think about how your scene looks, but you can use physically based rendering on mobile. You just have to use it wisely. Use it where it counts, use it where it's close to you, use it at the right range that is applicable. But where you can, use cheaper shaders. You can get some great effects with lots of different shaders that don't cost quite as much for every scenario. For this particular demo, we took the Adam project and we wanted to try and create a mobile VR experience from it. So you're like, you guys are crazy, right? Have you seen the size of the machine running the demo? And we're going to turn it onto a mobile phone, and then we're going to walk through. But it was a hack week, so what do you try and do? We try and hack. So we took the scene. We kept the standard shader on the Adam model. If I start that one there. But I've skipped ahead one too far. Excuse me a second. But what we wanted to do was to try and enable a fully surrounded map of everything that was happening in that scene to create the illusion of that experience. I'll come back to that in a second. So what are the kind of tools you can use to create these smoke and mirrors? Well, you can bake your environment. So this example, you can use a reflection probe in your Unity scene at the relevant camera position to bake a custom reflection probe that will output an EXR file for you. So that's a very quick way of making a nice high dynamic range cube map for your environment to load back into another scene that doesn't have all that polygon detail in it. So this short video is showing you the project of doing that, the process of doing that. You can set your reflection probe to custom in the inspector, set your resolution high, and click Bake, and Unity will prompt to save that file on disk for you. Make sure you remember what that is, and you can come back and grab it in a minute. And then you hide all that first range geometry that you don't want to render. So you're talking about your mid-level mountains and your detailed terrains that you've loaded into your scene. Think about using Unity as an art content tool. Load everything you want from the asset store, create all the crazy stuff you want in the trains. At the end of the day, you can bake all that out into a lovely environment map to use. Then, in your game scene, load your environment, and then take out all of that expensive geometry in the background. What you want to do is create a skybox material, and then you can assign that EXR cube map you've already generated in Unity, like so. And then in your lighting window, under environment lighting, you can select that created material as your skybox. And then, hey presto, all of that beautiful distance geometry is now loaded into your scene without the cost of any of those polygons. So, thank you. If you think that's clever, what happens when you start to want dynamic content in your backgrounds? What happens when you start to think about the Adam demo, for example, where the character is walking through the scene and things are changing all around? It's not a static backdrop. It's a change of time of day, or it's a change of special effects in the background. So this is when we get into the realms of, let's call it super cheating, if you like. we use a static environment map, but it's not sufficient for all that dynamic content that we want. So in the Adam Hack project on the Gear VR, we rendered a stereoscopic 360 video with VR Panorama, one of the plugins for Unity, from the perspective of Adam's head as he wandered through the scene. Now, you consider that's dynamic. Obviously, it's linear dynamic because he's taking a journey through the project. But then in order to put that back into the scene, we loaded that 360 video and projected it onto 2 spheres that are attached to Adam. So there's a 3D mesh of Adam walking through with the VR scene with everything else rendered stereoscopically from his point of view. And that is a nice, simple way, I say simple, it takes a bit of setting up and a bit of synchronization, to create dynamic 360 environment cubes that can then add dynamic content at very little cost in addition to your foreground 3D stuff. So give that a try if you can. Popping up my internet again. 1 second. So, what are the limitations? Well, you've got to think about the positional head tracking considerations. On the Gear VR, that's not so much a problem because you're looking around, your point of view is fixed. And that's why a lot of these cheating techniques of bringing AAA quality backdrops into what you're doing work, because you know where the perspective of the user is going to be at any given time. So what you need to consider is that what's been baked not moving when the head is translating will feel far away, and the actual geometry can feel disconnected. So it's all about understanding where the point of view of the user is in this case. If there's no positional head tracking, for example, cardboard and Gear VR, then the environment map on the skybox will fit perfectly to match the geometry. The same with 360 video. To do this with Oculus and Vive, for example, then you'd need to simulate that by setting the camera parent game object scale to 0, and then you can deactivate the positional head tracking. So what that is to say is if you've tried this for your Gear VR project, and you're like, well, why can't I do that on my higher-end VR project? Well, you can. You just need to consider that the positional tracking of the head is relevant here. So where do we go from here? Well, it's all about trying to create the most compelling visuals with the most limited resources. Obviously, the future of this, in terms of content generation, is definitely photogrammetry. And here's a very short video from another Hack Week project from the same week that Joachim and his crew were working on that shows the stunning possibilities of reducing a mesh from thousands of polys to very few polys, and then using that to populate an entire city. So once you've generated a point cloud and rendered to texture what you can see from here, you can generate a very low poly mesh and then use that in the LOD system to load dynamically throughout your scene. In this case, a very low-res unwrapped texture. Unity obviously has the possibility to do unwrapping. This is a project that might be available sometime in the future, but it's a kind of demo. There's lots of photogrammetry tools out there. Here we go, a city block of 1.5 million triangles down to 5,000. Looking pretty sweet. So, for the dessert, take a tasty poly reduction method. Use poly reduction tools that you can find, industry standard things that can plug into Unity or third-party tools, so that you can generate a suite of level of detail models for the kind of scenes that you're creating. That's really, really crucial when you think about the range of perceptions that we talked about earlier, because you can control those at specific distances. Reduce the texture sizes and obviously atlas them. So that means you have a bigger texture in the long run, but you have less of them. Then you've got less draw calls, you've got less, you've got less use of rendering all those individual materials all over the place. Limit your shader variants and expensive shaders. So don't just change the type of shaders, just use less different types as well, because the complication of that can lead to draw calls that are picking up stuff from all over your scene. Obviously, make sure you can use those LOD groups we talked about. Sprite sheet animations instead of many particles. So if you're doing particles, think very much about whether you can use meshes to represent those little raindrops or to represent those, because anything that's semi-transparent has an overdraw consideration. Likewise, when you're doing special effects, one texture page of an entire flame animation is a much better idea than lots and lots of little semi-transparent effects there. And again, 3D meshes instead of billboards for the win. So, eventually, we did it. We managed to get content running on the Gear VR for a number of these demos. And if I can click on that second video, it should. There we go. And the conclusion for this one, obviously you can see the Gear VR one. We've attached this video cubes to Adam's character there, and you can see we've rendered out some 360 video. And the eventual idea for that was that you could then put on the headset and experience an Adam demo from the perspective of 360 degrees virtual reality. I won't say it was altogether pleasant, because it was designed as a linear experience for film, and we've put your head straight in the place of Adam in that case. Suffice to say, it was a hack week, and that's what we do at Hack Weeks. We hack things. So, conclusions. Target your VR platform. Thinking about VR is a really broad term in terms of the performance of hardware that's available in the VR. If somebody says, oh, you're going to have to optimize this for VR, well, what are you talking about? Are you talking about supercomputer-driven, high-end VR headsets, or are you talking about, not pocket calculators, but you know what I mean, mobile phone-based VR? And this kind of broad scope of different VR platforms, if you can define earlier on where you're targeting, then you've got a really good chance of trying to figure out the scope of your work. From general rendering optimizations that we covered in the beginning of the talk, to brute optimization, where you turn lots of things off, to the real fancy smoke and mirrors. And when I say smoke and mirrors, I don't mean actual smoke and screen space reflections, if you can possibly avoid it. But you know what I'm saying. Things to obscure what's happening, to the full reauthoring of an entire project just for one particular portable VR platform. So along that scale, you can determine the balance between all of those different processes. And then you kind of understand the scope of your work a bit earlier on. Thank you very much. I have about 2 minutes for any questions. Please grab a mic if you've got anything to ask quickly.
Are particles with 1-bit alpha okay? Or would you prefer meshes?
They're not. On many mobile platforms, 1-bit alpha cutout can actually be worse because of the way that it calculates on certain Android and iOS platforms, for example. So we always advise, if you look at our sprite sheet editor, it will cut out to optimize that, because all that invisible mesh, it can depend on how that texture's authored as well, and how much blank space there is, but it's always a better rule of thumb to use mesh for those kind of shapes.
Okay, thanks.
Hi.
Hi. So when you were talking about making a video out of the entire environment and having it move through the scene, how would that work with VR? Would it just not work with being able to move your head and like slightly shift
with head tracking?
Positions? Yeah.
Yeah. Well, because we were targeting a particular platform in this case, we didn't have to deal with the concept of the head moving around. But there would be ways to try and offset that movement. It's all about understanding the perception and the range of disconnect between what's happening in the foreground and the background. For a project where the head position is fixed, that's not an issue. For others, it's about applying what you can to that special range and understanding how you blend between those ranges. Any more questions? OK, I've been Olly Nicholson. Thank you very much.